using the number pi, you're using the imaginary part of a complex number. So it's not just that it's a fancy or it's not just that it's an interesting concept, it's actually a very useful tool in mathematics, so there's a good reason for us to learn how to use it and to work with it. That's the intent of the videos to come, is to show all the various applications. We'll show you how to find the derivative and the integral of exponential functions as well at the end. And that's why we're in a series on complex numbers. So welcome to our lecture online. Sometimes you're faced with an infinite sum like this, and you wonder, how do you tell that it converges or diverges? So that's the question. Does it converge or does it diverge? Well, what you can see is that it looks very similar to something like this. So it is similar to the following. An infinite sum from n equals 1 to infinity of 3n to the 4th divided by n to the 5th. And we drop out the other two terms in the numerator and the other two terms in the denominator. You may say, well, why do I do that? Why is it important? Well, it turns out as n becomes large, and it will become large quickly, n to the 5th and n to the 4th will far overpower the value that n to the 3rd and n to the 2nd will get, and especially 2 implied at the end. So they become significant very quickly, so only this drives the infinite series as n becomes large, and so therefore this will determine whether or not it converges or not. So when we look at that, we can say, well, this is equal to the infinite sum from n equals 1 to infinity of 3 times n to the 4th divided by n to the 5th, which is 1 over n. And now we have an infinite series of 3 times of the sum from n equals 1 to infinity of 1 over n, which is equal to 3 times 1 over 1 plus 1 over 2 plus 1 over 3 plus and so forth. And we know that that series does not converge. So if that doesn't converge, having those small sums at the end will not make any difference. It will not converge anyway. So therefore, we say that this series will diverge. And again, using the comparison is often a very good way of keeping from trying to something very difficult and turning it into something that's rather simple. And that's how this done. Next, we want to find the moment of inertia of a triangle. And then we realize that the triangle can be positioned in two different ways. We can have a triangle like this, and then we try to find the moment of inertia relative to the x-axis. And of course, we realize that most of the area, as it would be if we had an object with mass, most of the mass is close to the axis of rotation, so therefore we expect a smaller moment of inertia relative to the x-axis. We could also have the triangle situated like this, with most of its area, or most of its mass, far away from the x-axis. So even though these triangles have the exact same area, just having them situated differently, you realize you're going to end up with a different moment of inertia. The moment of inertia of this one relative to the x-axis is expected to be larger. The question is, how much larger? What are the moments of inertia? Well, we're going to start with the top triangle first, and then the next video we'll do the bottom triangle to see how they differ. So we're going to find the moment of inertia of this triangle. Here we have a small area element called dA, which has the width x and the height dy. The equation here is the equation y equals nx plus d from algebra. But the slope in this case is going to be a minus slope, negative rise over run, so minus h over b times x plus d. My intercept of h. We're going to need that equation solved in terms of x, so that it's right here, x is equal to b minus b over h times y. So now we're ready to find the moment of inertia relative to the x-axis. So I sub x is equal to the integral. We're going to integrate over all these little area elements from y equals 0 to y equals h, from 0 to h of the distance squared, that would be y squared, times the area elements dA. Plugging in what dA is equal to, this becomes equal to the integral from 0 to h of y squared, and dA is going to be x times dy. Here's where we're going to need to find the value of x in terms of y, because we have the differential as dy, so we're going to plug in that value right there. So this is equal to the integral from 0 to h of y squared times what x is equal to in terms of y, which is d minus b over h times y times dy. And now we realize we're going to end up with two different integrals, so let's separate them. h, and now we have a y times the y squared, that's y cubed, times dy. So those integrals can be readily integrated. So this becomes equal to, the first one becomes b times y cubed over 3 evaluated from 0 to h. The second one becomes minus b over h times y to the 4th over 4 evaluated from 0 to h. Of course, when we're putting the lower limits, we get 0. When we're putting the upper limits, we get the following. On the first one, we get 1/3 b times h cubed minus, and notice that action would be the moment of inertia if this action would be in a rectangle of width b and height h. So we subtract from that this quantity right here, which is 1/4 b over h times h to the 4th power. You can see that this h will cancel out one of those, so this ends up being 1/3 bh cubed minus 1/4 bh cubed. Now the denominator would be 12. That gives us 4. So this is equal to 4 over 12 bh cubed minus 3 over 12 bh cubed, which is equal to 1/12 bh cubed. But now let's solve it in terms of the area of that rectangle, or triangle, I should say, not rectangle, triangle. So this is equal to, now we know that the area of the triangle would be 1/2 the base times the height, so it would be 1 over 6 times 1 over 2 base times the height, and then we have left the h squared, and so this becomes equal to 1/6 the area of the triangle times h squared, and that would be the moment of inertia of that triangle situated with the base against the x-axis and finding the moment of inertia relative to the x-axis. So it's 1/6 the area times h squared. Well, let's write that down up here. So we have 1/6 the area times h squared as being the moment of inertia relative to the x-axis of the triangle situated like that. Now we'll do this again on the next video, on the second example where we have to turn the triangle upside down to see what we get this time. So that's how it's done. Sometimes we end up with an infinite sum that looks very similar to one that we can easily find the convergence or divergence of, and we can find the sum of. It seems here that this can be written to be smaller than the infinite sum for n equals 1 to infinity of 1 over 3 to the n power. That's because the denominator here is larger than the denominator here, so for every denominator in the series, the denominator here will be larger than the denominator there, which means the fraction will be smaller in each case, which means the left side is indeed smaller than the right side. Now, does that converge? Well, we can make that look like a geometric series, and let's go ahead and try to do that. So this can be written as the infinite sum of n equals 1 to infinity of the quantity 1 over 3 raised to the n power. That's exactly the same thing. There's 1 to the n power, no matter what n comes, so it's equal to 1. Which means we can then factor out 1/3, so this can then be written as 1/3, or still the sum, n equals 1 to infinity of 1/3 times 1 over 3 to the n minus 1 power, and now we have a geometric series. And now we can say that the ratio is equal to 1/3, and the constant a is also equal to 1/3. And then we can find the sum of that geometric series. So the sum is equal to a divided by 1 minus r, which is 1/3 divided by 1 minus a third, which is 1/3 divided by 2/3, which is equal to 1/2. So we know that this series converges to 1/2, which means this converges to 1/2. And since we know that the left side is less than the series here, and since this is equal to 1/2, we know that this must be equal to 1/2. So the sum of n equals 1 to infinity of 1 divided by 3 to the n plus 5 must be less than 1/2. So therefore, we know that it converges. So just go. Therefore, the series converges, and we know that the sum must be less than 1/2. So using a comparison test is something you're familiar with. Quite often, help you solve one you're not familiar with, and that's how it's done. line. In this video, we're going to find the moment of inertia of a hollow circle relative to the center mass of the circle. Assuming we're trying to find out what the moment of inertia would be as the circle in that direction. So we have an inner radius R1 and an outer radius R2, and we have a small area element dA that is small r away from the center with a thickness of dr. So the area of dA is equal to the circumference of 2 pi small r times dr. Also for reference, the area of the hollow circle would be equal to the area of the outside radius minus the area of the example. How do we find the moment of inertia? Well, to do that, we simply use the integral to say that the moment of inertia is equal to the times the area element. And we're going to integrate that from the inner radius to the outer radius, so from R1 to R2. So dA, the R is going to be written as of R squared times 2 pi R dr from R1 to R2, and we can take the 2 pi out. So this is 2 pi times the integral from R1 to R2 of R cubed dr. So now we're ready to integrate that. That's relatively easy. This becomes equal to 2 pi times R to the 4th divided by 4, evaluated from R1 to R2. Notice I can take the 1 over 4 out. 2 divided by 4 is 1 over 2. So this becomes equal to pi divided by 2 times, when I plug in the upper limit, I get R2 to the 4th power minus, when I plug in the lower limit, I get R1 to the 4th power. So that's the moment of inertia of a hollow circle. But let's take it one step further. Let's go ahead and factor what we have there. So that means that this becomes equal to pi divided by 2 times, and we have the difference of two quantities raised to the 4th power. So this can be written as R2 squared minus R1 squared multiplied times R2 squared plus R1 squared. And then we realize over here that pi times R2 squared minus R1 squared is actually the area of that hollow sphere, or that hollow circle. It's not a sphere, it's a circle. So pi times this is really the area of that circle. So what we can then do is we can go ahead and factor it out. So we have 1/2 times, like this is pi times R2 squared minus R1 squared, and then multiply that times R2 squared plus R1 squared. Now recognize that this here is simply the area of that hollow circle. And we can write this as 1/2 times the area of the hollow circle times R2 squared plus R1 squared. And this then becomes the moment of inertia of a hollow circle. Instead of using the mass, if we had an object with mass, that would become 1/2 m R2 squared plus R1 squared, or if you want to reverse order, it doesn't matter. So in this case, instead of having m, we're going to have area. The area of the hollow circle, so it's 1/2 times the area times R2 squared plus R1 squared. And that's the moment of inertia of a hollow circle rotating about its center of mass. And that's how it's done. Line. In order to solve an infinite series problem like this one, it can come in handy to use the technique of partial fractions. Well, first, let's see if we can kind of guess to see if this is going to converge. And this looks a lot like a T-series. If you remove the -1 in the denominator, and notice as n becomes very large, the n squared minus 1 in the denominator is almost exactly the same as n squared. That looks a lot like a T-series, and the exponent is greater than 1, so we expect this to converge. Now, what will be the sum? Well, we can find out what the sum will be by writing the following thing. This will be equal to the infinite sum of 2 divided by, and if we factor the denominator, we get n plus 1 times n minus 1. And then this lends itself to writing it as 2 separate fractions. So this can be written as the sum of a divided by n plus 1 plus b divided by n minus 1. And then we use the technique of partial fractions to solve for a and b, and then we can sum up the two infinite series separately. So how do we do that? Well, we can say that 2 is going to be equal to, when we multiply a times n minus 1, plus when we multiply b times minus 1. I should say b times n plus 1. What we're actually doing here is we're writing this over a common denominator of n plus 1 times n minus 1, which means that a times n minus 1 plus b times n plus 1 has to equal the numerator of that. Now we can solve this for a and b. So this, if we write this out, we say that 2 is equal to a times n minus a plus b times n plus b. And from that we can conclude that a plus b must equal 0, because there's no n counterpart on the left side of the equal sign, and we can say that minus a plus b is equal to 2. So that means that b is equal to minus a, and if I plug that in here, we have minus a is equal to 2, or minus 2a is equal to 2, or a is equal to minus 1. Oh, didn't write that right? Minus 1. There we go. So if a is equal to minus 1, and b is negative a, that means that b is equal to 1. Which means that this can now be written as the infinite sum of a, which is minus 1 over n plus 1, plus b, which is 1 over n minus 1. Alright, so now we're going to sum those up separately. And so we're going to get the sum has n equals 2 to infinity of minus 1 divided by n plus 1. This is going to equal 2. Starting with the first one, if n is equal to 2, we get minus 1 over 3, minus 1 over 4, minus 1 over 5, minus 1 over 6, and so forth. And then the second sum, to get from n equals 2 to infinity, and we take the second one, which is 1 over n minus 1, that would be 1 over n minus 1, might as well write it out. So starting with n equals 2, we get 1 over 1, plus 1 over 2, plus 1 over 3, plus 1 over 4, plus 1 over 5, plus and so forth. And now, I'm going to put a line here so I don't get confused. So now, since we have to add those two together to get the total sum, notice that after we get to the 1/3 part, we have a 1/3 here and a minus 1/3, a 1/4 and a minus 1/4, a 1/5 and a minus 1/5, meaning all these terms cancel out all those terms. Which means the only two surviving terms that do not get canceled out are those two, which means that this sum, which is the sum of these two series, so the sum n equals 2 to infinity of 2 over n squared minus 1 can be